Welcome to this in-row weeding supplement to our Vision Guidance training videos. I am Nick Tillett, and in this series of 6 presentations I'll be working with Kevin King to cover the extra information you need to implement our in-row Vision Guidance and control systems, which are designed to remove weeds growing between crop plants within rows and to treat individual crop plants. This introductory video is fairly general, covering some of our long history in this area and the basics of how our current systems work. The subsequent 5 videos are more specific and assume you are already familiar with our inter-row systems and have viewed our inter-row video tutorial series. After this introductory video, in subsequent video tutorials, we will examine the in-row specific hardware, explain the additional in-row user interface features, show how you might go about setting up a new in-row machine, and how to operate that machine in the field for the first time. And finally, in video 6, we will discuss how to use the configuration editor to configure additional in-row features. You can select the video you need from our website and view it as many times as you want. Whilst we had been thinking about the in-row weeding problem from the early 1990s, it was not until the year 2000 that we made our first practical steps with a small project that demonstrated feasibility, but highlighted many challenges, notably the difficulty of achieving good within-row cultivation coverage at high speed. It was clear that systems with reciprocating blades would always be a compromise between speed, input power, robustness, and soil throw. Furthermore, for any system with a fixed insertion and retraction speed, the area cultivated inevitably reduces as forward speed increases. That realization stimulated our idea for a continuously rotating blade, phase locked with plants as they were tracked through an image sequence. This avoids high accelerations, reducing input power and soil throw. If engineered correctly, it also makes cultivated area independent of forward speed. Furthermore, reduced accelerations mean the whole mechanism can be made heavier and stronger without a performance penalty. The trick was to design matching blade profiles and smooth dynamic paths that gave good coverage without crop damage. Of course, we also needed to extend our image analysis algorithms to robustly detect and track individual crop plants as well as crop rows. Development of our rotary blade technique started in earnest in 2005. The first rig was electrically driven but had limited power. So, for production machines, a hydraulic motor regulated by a proportional valve was employed to deal with the relatively harsh weeding environment. It is shown here in prototype form. The project was a success, and Garford Farm Machinery started selling hydraulically powered in-row machines using our technology in 2008. This video is an early example. At the request of a Californian customer, we also introduced the option to use the same machine running alternative software to thin salad crops, deliberately taking out unwanted plants to optimize spacing, as seen in this video, which dates back to 2008. These machines perform very well, but precise hydraulic proportional flow control comes with the necessity for large volumes of clean oil, which many tractors can struggle to supply. So, to improve energy efficiency and to avoid the need for expensive PTO-driven auxiliary hydraulic power packs, we undertook the development of an electrically driven variant. We use a powerful brushless motor coupled to a robust epicyclic gearbox. The result is a faster and more precise system that can rotate at up to 6 revolutions per second, though soil conditions normally dictate more modest speeds. The first commercial brushless rotor machine using our licensed technology was sold by Garford Farm Machinery in 2015. It is shown here cultivating 20 rows, demonstrating the feasibility of larger machines. In 2021, Tillett & Hague developed an improved rotor unit, reducing weight, simplifying setup, and improving reliability. We also now offer a complete modular wiring loop for ease of implementation and serviceability. At the same time, we had been developing systems for spot spraying individual broadleaf weeds in high-valued drill crops such as carrots and onions. See our separate video on that subject if you want to know more. We can apply some of that spray application technology to our in-row weeding system, allowing users to spot apply liquid inputs either between crop plants or onto crop plants. This can be done as a separate operation or done in conjunction with in-row cultivation. Examples include chemical thinning, as shown here, treating an area between crop plants with herbicide, avoiding the crop itself, applying crop protection agents, chemical or biological, onto crop foliage, application to the base of the stem, as shown here in this nematode drenching application. These approaches can result in large reductions in total application volume whilst maintaining efficacy. In response to customer demand, we've also developed a reciprocating blade controller to allow Tillett & Hague guidance to control reciprocating blade type in-row weeding machines, as shown here. This feature was added in 2021. We will now have a quick look at the principles behind how it works. In-row plant location and tracking is done with the same cameras used for inter-row applications. However, we match individual plants with a two-dimensional template representing the overall planting pattern rather than just linear crop rows. As plant pitch can be a bit variable, the template has some flexibility. In-row weeding requires every individual plant to be detected, and so it is necessary to view 100% of the cropped area with some margin around the outer rows. This constraint has implications for machine geometry and might require use of multiple cameras or wide-angle lenses to achieve the necessary coverage. For example, the 10 rows shown here can use 2 cameras, each viewing 5 rows, enabling all 10 rows to be tracked without the need for an excessively tall camera pole. Tracking individual crop plants is more sensitive to camera alignment than tracking crop rows. It is therefore normal to use automatic frame leveling to stabilize camera position. Our in-row controllers have such a system built in as standard. As the machine moves forward and new crop plants enter at the top of the image, their position is predicted based on the predetermined template and the position of other plants already detected in that row. The search is conducted using that predicted position as a starting point. Once a new plant is locked onto, it is tracked in successive video frames as it passes down the image. In each frame, a local search is conducted whose final position is indicated by a blue cross. If that local search does not find a good match, the cross will be coloured yellow. If the match is good but a long way from the expected position, it is coloured red. Those local individual plant matches are used to update a tracking algorithm whose plant positions are indicated by green crosses. Those green crosses are normally not visible as blue crosses are superimposed over them. But as plants get close to the bottom edge of the image, the blue crosses disappear, leaving the green crosses visible. From this point, plant position tracking out of the bottom of the image right back to the cultivators is done by dead reckoning. This puts more reliance on speed estimation than is the case for inter-row applications. Consequently, in-row machines are normally fitted with odometer wheels for accurate measurement of forward motion. At the same time, crop row position is also estimated so that lateral alignment can be maintained. Corrections to lateral position of the implement are carried out in the same manner as inter-row machines. Treatment devices such as rotors, actuators or nozzles are synchronized with individual plant tracks as they progress back out of the camera's field of view to the treatment device. This clip shows a rotor set to run above ground, demonstrating how rotors automatically adapt to variability in both plant spacing and tractor speed without changing the area cultivated. If required, multiple devices, for example nozzles and cultivators, can be set up on a single row, thus increasing overall efficiency. Our system is modular. All treatment devices communicate with the main implement module via our proprietary CAN bus protocol. Brushless electric rotor drives individually connect direct to the network. Solenoid valves for the control of hydraulic actuators or spray nozzles are driven from one of our multi-channel control boards, which are normally housed in a plastic enclosure and connected to the CAN network. In principle, all the geometries available for inter-row implements are also available for in-row machines. For example, front or rear mounted, in both side shifted or disc steered setups, and multiple section to track independently planted bouts. However, remember ours is a vision-based system, so there must always be space for the camera to see an adequate area of crop. You would not want to drive down the motorway looking through a letterbox, and similarly, our systems perform best when they have a good view of the crop. For optimal performance, implements should be designed as an integrated system. Tillett and Haig are very willing to engage with machinery designers, taking a holistic approach to facilitate that integration. Close collaboration speeds development, reduces costs, and increases performance. Our approach is based on template matching. The more accurate the template match, the better the performance. The system scales from large to small machines. Typically, we would expect guidance accuracy to be within 1 centimetre. In-row rotors have a maximum speed of about 5 plants per second per row. For plants at a 30 centimetre pitch, that equates to 1.5 metres per second or just over 5 kilometres per hour. Reciprocating blades are generally limited to about 2 plants per second. They can be made to run through the crop faster, but the blades do not have time to fully penetrate into the row, so the efficacy reduces as speed increases. So, to conclude, backed by over 25 years of research, we can offer implement manufacturers a range of guidance options for crop protection applications ranging from mechanical weeding, both within and between crop rows, to the precision application of sprays. We can offer systems for both electrically and hydraulically driven in-row rotors, along with suitable blade profiles. We can also provide control systems for reciprocation blade type in-row cultivators. It is also possible to control spot spray nozzles or applicators, either in combination with mechanical weeding or as a separate operation. We hope you found this presentation useful. Remember that it's the first part of a series of 6 videos that you can select from our website, which also has links to other reference and training material. If you have any questions, please get in touch. Thanks for watching.